Okay, let's unpack this. We're taking a deep dive into the world of climate today, how we classify it, understand its incredible diversity across the planet, and explore the powerful forces that are constantly changing it.
Right.
We've got a stack of notes and excerpts here that give us a fantastic foundation for this exploration. Our mission is to dig into these sources to really grasp the methods scientists use to categorize Earth's climate zones, look at the solid evidence showing climate has been shifting throughout history, and pin down the key drivers behind those changes, particularly the ones highlighted in the material.
And it's fascinating, isn't it? Climate is just this massively complex system. You've got temperature, precipitation, wind, so much more, and it varies everywhere.
Absolutely.
So bringing some kind of systematic order to that, well, that chaos, it's essential if we want to analyze it or compare regions or even, try to predict future conditions.
That makes total sense. You can't really study something so vast and variable without breaking it down somehow. So why do scientists actually bother classifying climate? What's the real point beyond just saying, oh, it's hot here or it's cold there?
Well, as the sources explain, it's really about creating these understandable units for description, for analysis.
Okay.
Think of it maybe like biology classifying species. You group things with similar characteristics to understand the whole picture better.
Right, like finding patterns.
Exactly. And the material here talks about 3 broad approaches for climate classification: empirical, genetic, and applied.
Empirical, genetic, applied. Okay, those sound pretty crucial. Can you quickly break those down based on what we've got here?
Sure. So empirical classification is purely based on what you observe, mostly temperature and precipitation data. You just measure the climate, then you categorize it.
Got it. Just the facts.
Right. Then genetic classification looks more at the causes of the climate. Factors like pressure systems, air masses, ocean currents, the why behind it.
Okay, so the underlying processes.
Precisely. And then applied classification is, well, it's designed for a very specific purpose, maybe for agriculture or building design, something practical like that.
Okay, so empirical is the what, genetic is the why, and applied is the for what. That helps. And the sources really seem to lean into the empirical side, focusing heavily on Köppen's scheme.
That's right. Köppen's system is presented here as the most widely used empirical method. His core insight, which was surprisingly early back in 1918, was recognizing this strong link between where certain types of natural vegetation grew.
Vegetation?
Yeah, and the climate conditions there. He actually used specific temperature and precipitation values, chosen because they seemed to correlate really well with the boundaries of major vegetation zones to define his climate types.
Wow. Okay, so the genius wasn't just crunching numbers, but connecting those numbers directly to what you can actually see: the plants, the ecosystems that thrive in different places.
Exactly right. It's an empirical system built on mean annual and monthly temperature and precipitation data, and it uses these combinations of capital and small letters to denote different types and subtypes.
Right, those codes you see on maps.
And the sources point out that despite its age, it was developed in 1918 and modified since, it's still remarkably popular and widely used today. It gives you a quick code that tells you a surprising amount about the fundamental conditions of a region.
It totally resonates. I mean, thinking about different parts of the world, you just intuitively know the landscapes are different, right? And this system gives us a concise way to map those differences globally based on those fundamental climate inputs.
Precisely.
All right, let's dive into Köppen's main categories then, the ones with the capital letters.
Right.
What are they based on, according to these sources?
So Köppen defined 5 major climate groups, mostly based on temperature characteristics, but with one really crucial exception. The humid climates are designated by capital letters A, C, D, and E. The big exception is Group B, that's based on precipitation, or really the lack of precipitation.
Oh, the dry ones.
Exactly. And then there's also an additional group, H, for highland climates, which are basically altitude dependent.
Okay, so A, C, D, E are humid, mostly about temperature. B is dry, and H is highland.
Got it. Can you give us the quick defining feature for each main group? I think there's a table in the notes, table 11.1.
Yeah, sure. Let's see. Group A, the tropical climates, they have an average temperature of the coldest month, that is 18 degrees C or higher. So consistently warm.
Okay, always warm.
Group B, dry climates, are defined by potential evaporation exceeding the total precipitation. Basically, more water could evaporate than actually falls as rain.
Makes sense for dry.
Group C, warm-temperate or mid-latitude climates. They have an average temperature of the coldest month that's somewhere between -3 degrees C and 18 degrees C, so mild winters.
Right, not extreme cold. Group D, cold snow forest climates, have an average temperature of the coldest month at -3 degrees C or below, getting properly cold in winter.
Definitely colder.
Group E, the polar climates, are the coldest. The average temperature for all months is below 10 degrees C.
Wow, never really warm.
Never warm. And Group H, Highland, well, that's just cold because of significant elevation. Mountains, basically.
Got it. That gives us the main framework, and then there are the smaller letters to add more detail, right?
Exactly. Within those main humid groups, A, C, and D, small letters tell you about precipitation patterns. So F means no dry season. M indicates a monsoon pattern, W means a winter dry season, and S means a summer dry season.
Okay, F, M, W, S for rain patterns.
Right. And then other small letters like A, B, C usually refine the temperature characteristics, often about how hot the summer is.
And B, the dry climates. They have their own special letters.
They do. Group B gets a special subclassification using capital letters. S for steppe, which is semi-arid, and W for desert, which is properly arid.
Okay. S for steppe, W for desert. That builds the code we see on climate maps, a capital letter for the main group, then smaller letters, or SW, to get more specific.
That's system.
Let's unpack some of these then, maybe starting with the tropical humid climates, Group A. What are the key features of those three types the sources mention? AF, AM, and AW.
Okay, Group A climates, you find them roughly between the tropics of Cancer and Capricorn. What really defines them is that consistent heat, the sun's high overhead pretty much year-round, and high humidity, often influenced by the ITCZ, the Intertropical Convergence Zone.
Right.
The really striking feature is the very low annual temperature range. Temperatures are high, and they just stay high. Very little seasonal variation in temp.
Okay, hot and humid all year.
Yeah.
And the three subdivisions.
F, tropical wet. This is closest to the equator. Think of the Amazon basin, Western Equatorial Africa, the East Indies. They get substantial rainfall basically every month, often those classic afternoon thunderstorms.
The rainforest climate.
Exactly. Temperatures are uniformly hot, maybe around 30 degrees E max, 20 degrees C min, day in, day out. Supports those dense tropical evergreen forests.
And AM, tropical monsoon.
AM is tropical monsoon. The sources point to places like the Indian subcontinent, parts of South America, northern Australia. These have really distinct wet and dry seasons. Very heavy rainfall concentrated in the summer, often driven by monsoon winds, and then a noticeably dry winter.
So a strong seasonal pulse of rain.
A very strong pulse. Then there's tropical wet and dry, sometimes called Savanna climate.
Okay.
This is usually found north and south of those AF zones. Think large parts of Brazil, Central Africa, Sudan. Rainfall here is generally less than an AF or AM, and it's more variable. You get a shorter wet season and a longer, more pronounced dry season.
Right, like the grasslands you see in documentaries.
Precisely. Temperatures are still high year-round, but you actually see the greatest daily temperature range during that long dry season. This climate supports deciduous forests, trees that lose their leaves, and, yes, grasslands. So even within the tropics, just how the rain falls through the year creates vastly different landscapes.
It really highlights how critical that precipitation seasonality is. Okay, let's swing to the opposite extreme, the dry climates, Group B. These cover a huge chunk of the planet, don't they?
They really do, roughly 15 degrees to 60 degree latitude north and south. The defining characteristic, of course, is very low precipitation, just not enough for substantial plant growth.
And why are they where they are? The sources mention a few reasons.
Yeah, several factors. At lower latitudes, say 15, 30 degrees, they're often located under those persistent subtropical high-pressure systems. Air is sinking there, which inhibits cloud formation and rain.
Right, the descending air suppresses rain.
Exactly. And coastal deserts in these latitudes often get intensified by cold ocean currents running along the western margins of continents. That cold water stabilizes the air above it.
Interesting. And in the mid-latitudes?
In the mid-latitudes, say 35, 60 degrees, dry climates tend to be deep in the interior of continents, just far away from oceanic moisture sources. Or they might be in the rain shadow of large mountain ranges.
So it's all about atmospheric circulation patterns and how far you are from water. And these are the ones divided into steppe S and desert W.
Correct. BS is subtropical steppe, and BWH is subtropical desert, typically found between 15-35 degree latitude.
What's the key difference between steppe and desert here?
Steppe is basically a transition zone. It gets slightly more rain than a true desert, maybe enough for some sparse grasses or shrubs, but that rainfall is highly variable. The sources note that even small variations year to year can have huge impacts, like causing severe drought and famine in steppe regions like the Sahel.
Right, living on the edge, climatically speaking.
Very much so. Deserts, BWH, get even less rain. When it does rain, it's often in really intense, localized thunderstorms, but the water runs off quickly and isn't very effective for soil moisture.
So brief floods, but still arid overall.
Yeah. Though the sources do mention that coastal fog can actually be a significant moisture source in some specific desert locations.
Okay. And temperatures. These must be hot.
Oh, yeah. Especially the subtropical ones. Temperatures can be extreme. The source actually notes the highest shade temperature ever officially recorded, 58 degrees C, which is about 136 degrees Fahrenheit,
Whoa.
was in Al-Ziza, Libya, which is a BWH climate, back in 1922. You also see very high annual temperature ranges and very large daily temperature ranges, hot days, cool
It's
night.
58 degrees Celsius. I can't even imagine that.
Wonderful.
Okay, what about the mid-latitude climates, Group C, the warm temperate ones?
Okay, Group C, warm temperate. These are generally located between 30 degrees and 50 degree latitude, often on the eastern and western edges of continents. They're characterized by distinct seasons, warm to hot summers, but relatively mild winters.
Milder than Group D, anyway.
Definitely. The sources list several types. CWA, CFE, CFB are mentioned.
Let's look at a couple of those. C's, the Mediterranean climate, is pretty famous.
Yes, CS is very distinct. Found, obviously, around the Mediterranean Sea, but also on other west coasts between about 30, 40 degree latitude like central California, central Chile, parts of coastal Australia.
Right. What's the key feature there?
The key is the seasonal shift in pressure systems. In summer, they're under the influence of the subtropical high, which brings stable, sinking air, leading to hot, very dry conditions.
Classic dry summer.
Exactly. But in winter, the wind belts shift, and these areas come under the influence of the mid-latitude westerlies, which brings storms and moisture. So you get mild, rainy winters, summer average temps around 25 degrees C, winters maybe below 10 degrees C. Precipitation is moderate, maybe 35, 90 centimeters, but almost all of it falls in that winter half of the year.
That strong seasonal rainfall pattern is really the defining thing. Okay, how about CFI, humid subtropical? Often found on the East Coast, right?
That's right. CFAC climates are typically on the eastern sides of continents in subtropical latitudes. Think eastern USA, southern and eastern China, southern Japan, parts of South America, southeastern Africa, eastern Australia.
Okay, quite widespread. How are they different from Mediterranean?
The big difference is rainfall. Unlike the Mediterranean's dry summer, CFA climates generally have rainfall year-round. This is often due to unstable air masses moving in from the ocean. You get frequent summer thunderstorms and also precipitation from frontal systems in winter.
So, always humid.
Pretty much. Precipitation is higher, typically 75, 150 centimeters annually. Summers are hot and humid, averaging around 27 degrees C, and winters are mild, maybe 5, 12 degrees C. Because of the humidity, the daily temperature range tends to be relatively small compared to drier climates.
Makes sense. And one more from Group C, CFB, the marine West Coast climate. Found poleward of the Mediterranean type on west coasts.
Yes, CFB climates are poleward of seas, typically on west coasts. Think northwestern Europe, the Pacific Northwest of North America, north of California, southern Chile, southeastern Australia, New Zealand.
What's the dominant influence there?
The ocean. The strong marine influence keeps temperatures very moderate all year round. Summers are generally cool, maybe 15, 20 degrees C average, and winters are surprisingly mild for their latitude, often averaging 4, 10 degrees C. Both the annual and daily temperature ranges are typically quite small.
And rainfall.
Precipitation usually occurs throughout the year thanks to frequent cyclonic storms moving in from the ocean. The total amount can vary a lot, though, anywhere from 50 centimeters to over 250 centimeters, depending on location and topography.
You can definitely picture those places, Seattle, London, maybe. Knowing these codes really does give you a useful shorthand for the typical weather and even the kind of landscape you'd expect.
It's a very practical system in that way.
Okay, let's move into the colder regions now, groups D and E. Starting with D, the cold snow forest climates.
Right, Group D. These cover huge continental areas, primarily in the northern hemisphere, between roughly 40 degrees and 70 degrees north latitude. Think vast stretches of Europe, Asia, and North America.
What defines them?
They're characterized by severely cold, snowy winters and relatively short summers, though summers can still be warm. The sources mention two main types. DF, which has humid winters, meaning precipitation year-round, and DDO, which has distinctly dry winters.
And they get colder as you go north.
Generally, yes.
Right.
The severity definitely increases poleward. Winters are long and cold, often with persistent snow cover. The frost-free or growing season is quite short. One key feature is very large annual temperature ranges, big swings between summer and winter. And the weather can change very abruptly.
That DDO type, cold climate with dry winters, sounds particularly harsh. Where is that mostly found?
DDO is prominent mainly in northeastern Asia.
Yeah.
What happens there is a very strong high-pressure system, an anticyclone, develops over the cold continent in winter, which suppresses snowfall and makes the winters very dry. Then in summer, there's a sort of monsoon-like reversal with winds bringing some moisture inland.
And the temperatures.
Temperatures are extreme. As you go poleward within the DDO zones, summers get cooler, but the winters become intensely cold. The sources say many locations average below freezing for up to 7 months of the year.
Wow, 7 months below freezing.
Yeah. And despite the summer precipitation, the total annual amount is often quite low, maybe only 12, 15 centimeters in some areas. Brutal cold, but not necessarily huge amounts of snow overall.
That does sound harsh. Okay, then even colder are the polar climates, Group E.
That's right. Polar climates, Group E, are found poleward of about 70-degree latitude. The sources divide these into two types, ET, which is tundra, and EF, which is ice cap.
ET, tundra. What's that like?
Tundra climate, ET, is actually named after the typical vegetation low-growing things like mosses, lichens, sedges, some flowering plants. A really key feature here is permafrost.
Ah, the permanently frozen ground.
Exactly. The subsoil is permanently frozen, often to great depths. Only the very top layer, the active layer, thaws during the short, cool summer. This short growing season and the fact that meltwater can't drain down through the frozen ground, leading to waterlogging limits vegetation to these low-growing forms. But interestingly, summers have incredibly long daylight hours.
Right, the midnight sun effect. And EF, ice cap?
Yeah.
That sounds like the ultimate cold.
It pretty much is. Ice cap climate, EF, covers the vast interior ice sheets of Greenland and Antarctica. Here, the average temperature is below freezing even in the warmest summer month.
Constantly frozen.
Constantly frozen. Precipitation is actually minimal, very, very low. But whatever falls is snow, and it never melts. It just accumulates year after year, century after century, compressing under its own weight to form those massive ice sheets. The sources mention Plateau Station in Antarctica as an example of this climate.
These really are Earth's frozen extremes. And finally, just briefly, the H group for Highland climates. How do they fit in?
Highland climates, H, are a bit different because they aren't defined by latitude, but primarily by topography, by mountains. In mountainous regions, altitude becomes the dominant climate control.
So temperature drops as you go up.
Rapidly, yes.
Yeah.
You get large temperature changes over very short horizontal distances just because of elevation changes. Precipitation patterns are also highly variable, influenced by slope aspect and position relative to prevailing winds. What you get is a distinct vertical zonation of climate types. As you ascend a high mountain, you can pass through conditions similar to several different Köppen zones found at sea level across different latitudes.
Fascinating, like climbing through climate zones.
Exactly.
Okay, so that's a great overview of Köppen's system.
Yeah.
A really useful way to map and understand the world's diverse climates. But the sources quickly pivot from this classification to a really critical point. Climate changes.
Right.
Is this idea of climate change a new thing, or has it always been happening?
That's a vital question, and the sources address it directly. They state very clearly that climate change is a natural and continuous process. Earth's climate has always been changing throughout its incredibly long history. The intense focus now sometimes makes it seem like a modern invention, but it's definitely not.
So the planet's climate system is naturally dynamic. What kind of evidence do the sources actually present for these past natural shifts?
The material lists several lines of evidence. Geological records are key. They show these repeated alterations between glacial periods, ice ages, and warmer interglacial periods like the one we're in now.
How do we see that in the rocks?
Well, in areas that were once covered by ice sheets, particularly in high altitudes or high latitudes, you see specific landforms, geomorphological traces left behind by glaciers advancing and retreating, things like moraines, U-shaped valleys. Also, sediment layers deposited in glacial lakes contain evidence, like pollen or sediment type, that shows past warm and cold cycles.
Okay, physical scars on the land and layers in lakes. What else?
Tree rings are another valuable tool mentioned. They can provide clues about past wet and dry periods, sometimes going back hundreds or even thousands of years, depending on the tree species and location.
Right, the width of the rings.
Exactly. Wider rings generally mean better growing conditions, often wetter or warmer, and even historical records can be useful. Things like accounts of crop yields or failures, major floods, documented migrations of people. These can sometimes reflect significant climate variations experienced by past societies.
So the Earth's climate is inherently dynamic, always shifting. The sources even give some specific examples of these past changes, right?
Yes, they really emphasize that variability is constant. For instance, they mention archaeological findings suggesting the Rajasthan desert region in India was actually wet and cool around 8000 BC.
Wow, quite different from today.
Very different. And later, the Harappan civilization, which flourished from about 3000 to 1700 BC, was centered in a region that apparently had significantly higher rainfall than it does now. The sources say dry conditions seem to have increased there since around 1700 BC.
And on longer timescales.
On a much larger geological scale, the sources note the Earth was generally very warm between 500 and 300 million years ago. More recently, during the Pleistocene epoch, the last couple of million years, there were multiple cycles of major glacials and interglacials. The peak of the last major ice age was about 18,000 years ago.
And we're in an interglacial now.
Yes, our current warm interglacial period is thought to have begun about 10,000 years ago.
It's incredible to think about those immense timescales and shifts. What about closer to our own time? The sources mention more recent ups and downs, too.
Definitely. Variability happens on shorter timescales, too. The sources note the 1990s, for instance, witnessed quite a few extreme weather events, recorded the warmest global temperatures of the century up to that point, and also saw significant floods in various places.
Okay.
They also cite specific events like the devastating Sahel drought in Africa from 1967 to 1977, and the Dust Bowl period in the U.S. Great Plains during the 1930s.
Right, historical droughts.
And even further back in Europe, you see these episodes like the period when Vikings were able to settle Greenland during a relatively warmer spell in the 10th and 11th centuries. That's often contrasted with the Little Ice Age, a generally cooler period that affected Europe and North America from roughly 1550 to 1850.
So warming, cooling, droughts.
Yeah.
It's always been happening.
It seems so. The sources also mention a general upward trend in global temperatures, observed from around 1885 up to about 1940, followed by a period of slight cooling, which was apparently more noticeable in the northern hemisphere after 1940 for a few decades.
That's fascinating history, but the sources really seem to emphasize a specific, strong warming trend in the 20th century that perhaps scans out from this background variability. Is that fair to say?
That's absolutely the impression given in the material. They state the annual average near-surface temperature of the world is around 14 degrees C, and they note a very clear increasing trend throughout the 20th century.
And they pinpoint specific periods.
Yes, the periods of greatest warming in the 20th century are specified as 1901 to 1944, and then again from 1977 to 1999. In each of those spans, global temperatures rose by about 0.4 degrees C.
0.4 degrees in just a few decades.
Yeah.
Twice.
Right. And here's a really critical point highlighted in the sources. Globally averaged, the annual mean temperature at the end of the 20th century was approximately 0.6 degrees C higher than it was at the end of the 19th century.
Okay, a rise of 0.6 degrees C over that century. That might not sound like a huge number in isolation, but the sources seem to highlight the speed of that rise and maybe the clustering of warmth recently.
Exactly. That's the context they provide.
Yeah.
They point out that of all the warmest years recorded globally between 1856 and the year 2000, 7 of them occurred in just that final decade, the 1990s.
7 of the top warmest years in just 10 years.
Yeah. And 1998 was specifically singled out in the material as the warmest year of the entire 20th century, and potentially the warmest of the whole millennium up to that point.
Okay, so the key insight here, drawing from this evidence presented, seems to be that while climate naturally shifts over all sorts of timescales due to these geological and astronomical factors we touched on, the warming observed in the last century, particularly its speed and magnitude compared to these natural cycles, and the more recent historical examples like the Little Ice Age, appears distinct.
That's the strong implication from the source material provided.
So what actually causes these powerful climate shifts? Both the long-term natural ones and this more recent trend that the sources highlight.
The sources group the causes into 2 main categories: astronomical factors and terrestrial factors. Things from space, and things on Earth.
Okay, let's start with the astronomical ones. What's happening out there that affects us?
Well, one potential factor discussed is changes in the sun's output, specifically linked to sunspot activity. Sunspots are those darker, cooler patches on the sun's surface, and their numbers increase and decrease in cycles, roughly 11 years, but it varies.
Right. And how might that affect climate?
The sources mention that some researchers have suggested a possible link. Maybe periods with more sunspots correlate with slightly cooler, wetter, or stormier conditions on Earth, and periods with fewer sunspots correlate with warmer, drier conditions.
Interesting. Is that a strong link, though?
Well, here's where it's crucial to note exactly what the sources state. They say these findings connecting sunspots to significant climate variations are not statistically significant.
Ah, okay. So the idea's out there, but the evidence presented here doesn't strongly support it as a major climate driver. That's an important qualification.
It is. The material presents it, but adds that important caveat about statistical significance.
Okay. What other astronomical causes are mentioned?
The other main astronomical theory discussed involves what are called Milankovitch oscillations.
Milankovitch. Okay, what are those?
These are very slow, long-term cycles. We're talking tens of thousands, even hundreds of thousands of years in Earth's orbital characteristics.
How Earth moves around the sun.
Exactly. Things like variations in the shape of Earth's orbit, whether it's more circular or more elliptical, changes in the tilt of Earth's axis relative to its orbit, and the wobble of the axis, like a spinning top slowing down.
And these slow cycles affect climate how?
They subtly alter the amount and the geographical distribution of incoming solar radiation, what scientists call insolation, that reaches Earth's surface over these long timescales. The idea is that these long-term changes in sunlight patterns might be a key driver behind the major ice age cycles.
Okay, so really long-term, subtle changes in how our planet moves through space affecting the energy balance. Now, what about terrestrial causes? Things happening right here on Earth.
On Earth itself, a significant natural driver mentioned is volcanism. Major volcanic eruptions can inject enormous amounts of aerosols, tiny particles, and dust high up into the stratosphere.
Like ash clouds.
Exactly, and these particles can linger up there for months, sometimes even a few years, reflecting some sunlight back to space and reducing the amount of solar radiation that reaches the surface. This can lead to a temporary global cooling effect.
Do they give examples?
Yes, the sources specifically mention the eruptions of Mount Pinatubo in 1991 and El Chichon in 1982 as examples that cause noticeable, though temporary, global cooling.
So natural factors like Earth's orbit, maybe solar activity, though the link is weak here, and definitely volcanoes can shift climate.
Right.
But the sources seem to identify one particular cause as being especially important for the current warming trend we discussed earlier.
They certainly do. After discussing these natural factors, the sources state pretty clearly that the most important cause, particularly relating to recent warming, is considered to be the anthropogenic effect.
Anthropogenic, meaning human-caused.
Yes, human activity. Specifically, they point to the increasing concentration of greenhouse gases in the atmosphere resulting from human activities as the likely primary driver of the observed global warming.
Okay, that's a really key finding presented here in this material. While natural forces operate, human activity is singled out as the dominant factor in the current observed change. Let's really zero in on that then.
Huh?
Global warming and greenhouse gases. How do the sources explain the basic mechanism?
Well, global warming, as defined right here in the sources, is the observed warming of Earth's average global temperature, and it's attributed primarily to this increased concentration of greenhouse gases in the atmosphere.
And it works through the greenhouse effect, right? How is that explained?
Yeah, the analogy used is the atmosphere behaving somewhat like a greenhouse. It's largely transparent to the incoming shortwave solar radiation sunlight passes through easily and warms the Earth's surface.
Okay, light comes in.
Right. Then, the warmed Earth's surface radiates energy back upwards, but this is in the form of long-wave radiation or heat. This is where the greenhouse gases become really important. They are effective at absorbing much of this outgoing long-wave radiation.
So they trap the heat trying to escape.
Essentially, yes. They absorb it and re-radiate some of it back down towards the surface, trapping heat in the lower atmosphere and causing it to warm up. The sources use analogies you've probably heard. A glass greenhouse lets sunlight in but traps heat inside. Or even just getting into a closed car or bus that's been sitting in the sun, you feel how much hotter it is inside. That's a similar trapping effect.
That makes sense. So specific gases in the atmosphere are particularly good at absorbing that outgoing heat energy. Which ones are listed as the primary greenhouse gases of concern in these notes?
The main ones listed are carbon dioxide, or CO2, chlorofluorocarbons, CFCs, methane, CH4, nitrous oxide, N2O, and ozone, O3 specifically, ozone that's found down here in the troposphere, the lower atmosphere.
Okay, CO2, CFCs, methane, nitrous oxide, and tropospheric ozone.
Right. The sources also mention that other gases, like nitric oxide, NO, and carbon monoxide, CO, while maybe not major greenhouse gases themselves, can react chemically in the atmosphere in ways that affect the concentrations of the main greenhouse gases.
So it's a complex chemical mix up there. Are some of these gases more powerful heat trappers than others, molecule for molecule?
Yes, their effectiveness varies. It depends on a few things mentioned here. How much the concentration of the gas has increased, how long the molecule typically survives in the atmosphere its lifetime, and the specific wavelengths of long-wave radiation it absorbs most effectively.
Okay.
CFCs, for instance, are noted as being highly effective absorbers on a per-molecule basis. Tropospheric ozone is also mentioned as being quite effective at absorbing terrestrial radiation. And that lifetime point is important. A gas with a longer lifetime will continue to exert a warming influence for a longer period, meaning the atmospheric system takes longer to recover even if emissions stop.
Let's look at carbon dioxide, CO2, for a moment. The sources say it's present in the largest concentration among these main greenhouse gases.
Yes, CO2 is highlighted as having the largest concentration. And the primary source of its increase in the atmosphere, according to this material, is the combustion of fossil fuels burning oil, natural gas, and coal, mainly for energy.
Okay, burning fossil fuels.
Right. Another factor mentioned is land use changes, particularly deforestation. Forests act as natural sinks because trees absorb CO2 from the atmosphere as they grow. So clearing forests reduces that uptake capacity and can also release stored carbon.
So fewer trees mean more CO2 stays in the air. How long does CO2 actually stick around up there?
The sources estimate what they call the atmospheric adjustment time for CO2 is roughly 20 to 50 years. That's how long it takes for levels to stabilize after a change in emissions or uptake. And currently, the concentration is noted as rising by about 0.5% per year.
0.5% per year. And they mentioned doubling CO2 levels.
Yes, the concept of doubling the pre-industrial concentration of CO2 is often used as a kind of benchmark or index in climate modeling studies to understand the potential magnitude of future warming.
Okay. Now, what about CFCs? You mentioned they're highly effective, and they have another impact too, right? Related to the ozone layer.
They do. It's a dual issue. CFCs are highlighted here as being entirely products of human activity. They don't occur naturally. They are potent greenhouse gases themselves, but they also have the major problem that when they drift up into the stratosphere, the upper atmosphere, they catalytically destroy ozone molecules.
And stratospheric ozone is the good ozone.
Yes, the ozone layer up there is vital because it absorbs most of the harmful ultraviolet or UV radiation coming from the sun. The sources specifically mention the well-known ozone hole that forms over Antarctica as an area of significant ozone depletion, which allows more harmful UV rays to pass through to the surface.
So CFCs warm the planet and damage the UV shield. That's not good.
That's right, ideal, no?
Given these concerns about greenhouse gases, have there been international efforts to try and address the emissions, according to the sources?
Yes, the sources do mention international efforts, specifically highlighting the Kyoto Protocol. It was an international treaty agreed upon back in 1997, and it came into force in 2005 after enough countries had ratified it. 141 nations eventually did.
And what did Kyoto aim to do?
Its main goal was to legally bind 35 industrialized countries, plus the European community, to collectively reduce their emissions of major greenhouse gases. The target was set at an average of 5% below their 1990 emission levels, to be achieved by the period 2008-2012. It's presented here as a significant global recognition of the problem and an attempt to start mitigation efforts.
Okay, so there have been international efforts. But the sources also lay out some pretty serious potential adverse effects if this global warming trend continues. What are the major concerns raised?
The sources stress a couple of key points here. One is that once significant global warming really sets in, it could be very difficult, perhaps even impossible within human timescales to reverse.
Hard to undo.
Right. And the effects might not be uniform across the globe. Some areas could be affected much more than others, but the overall impact would likely be detrimental to Earth's life support systems.
Are there specific impacts they focus on?
A major specific concern that's highlighted is the potential for significant rise in global sea level.
Okay, how would that happen?
Two main mechanisms are mentioned. First, the melting of glaciers and polar ice caps would add more water volume to the oceans. Second, and perhaps equally important according to some studies, is the thermal expansion of seawater itself. As the ocean water warms, it expands and takes up more space.
Just like mercury in a thermometer.
Exactly the same principle. Warmer water is less dense and occupies a larger volume.
And the consequence of rising sea levels is pretty obvious, I suppose.
It is. The sources warn that a significant rise in sea level could inundate large areas of low-lying coastal regions and many islands around the world.
Which would displace millions of people.
Absolutely. This isn't presented just as an environmental issue. The sources explicitly state it would lead to serious social problems, forced migration, loss of land and infrastructure, and significant challenges for the entire world community. They actually use the phrase serious concern for the world community right near the end of the section.
That phrase, serious concern for the world community, and the potential for these difficult-to-reverse changes like widespread coastal inundation, it really does hit home, doesn't it?
It does.
Thinking about everything we've covered, starting with how we classify the world's incredibly diverse climates using systems like Köppen's, then looking at the long history of natural climate shifts over millennia, but then really focusing on the findings presented here about the recent rapid human-driven warming trend, largely from greenhouse gases, and its potential consequences like that sea level rise example. What does that final point from the sources, that call to the world community, really mean for the idea of building or maintaining a livable world for future generations?
That's a really profound question to end on, isn't it? If the analysis presented in these sources is accurate, that current trends, primarily driven by human activity, could indeed lead to potentially irreversible consequences on a global scale, like fundamentally changing coastlines and displacing populations, then the challenge of ensuring a livable world becomes much more complex. It's not just about adapting to the conditions we have now.
Right. It's about the future trajectory.
Exactly. It seems to imply a really deep need to consider the long-term, maybe even centuries-long, impacts of our current actions on the fundamental planetary systems we rely on. And perhaps it suggests we might even need to fundamentally rethink where and how human societies can sustainably exist, especially in those areas identified as most vulnerable to these projected changes like sea level rise. It frames the climate challenge discussed here not just as, say, an environmental problem or an economic one, but really as a fundamental question of future human geography, societal resilience, and maybe even intergenerational justice.
That's a powerful way to synthesize it, taking the specific data points and concerns from the sources, the classifications, the historical context, the warming trend, the sea level threat, and connecting them to that much bigger, longer-term picture of human future on this planet. We've certainly journeyed a long way today from V. Köppen's climate codes to the complex dance of natural climate drivers, and ultimately to the findings presented here about the significant and frankly, concerning role of human-caused greenhouse gas emissions and their potential far-reaching impacts.
It really underscores the profound interconnectedness of Earth's systems, doesn't it? And also the unique nature of the challenge presented by the scale and particularly the speed of the recent changes documented in these sources.
Absolutely. And of course, for everyone listening, remember, this has been our deep dive into the specific material we had in front of us today. On a topic this vast and vital, there's always more to explore, more perspectives to consider.